Hello all, welcome back. Today we will be continuing with our liquid propellant rocket motors part 2 as a part of your aerospace propulsion course. So continuing with our previous topic, that is your ignition systems. Today we will be continuing with respect to your liquid propellant distribution systems. Right? Most commonly the used distribution system employs turbopumps to deliver the propellants to the injectors that are present in the combustion chamber at a high pressure as well as maintaining the high flow rate. The turbopumps are driven by hot gas generated in a separate combustion chamber, or also called as a gas generator. The basic idea is to have as many variants which seek to confer improvements in efficiency. There are a number of design problems to be overcome. Above all, such pumps have to be reliable over the life of the engine, and they do have to work under extreme conditions and at peak or maximum efficiency. The mass of the turbo machinery, which is also a part of the dead weight of the rocket and limits the achievable mass ratio. The total mass of the rocket engine seems small compared to that of the vehicle as well as the propellant at the liftoff. Once the propellant is exhausted, right, the rocket engine mass becomes a significant part of the total dry mass of the same vehicle. So, therefore, a strong incentive is to reduce the mass of the engine, particularly the rocket engine, as far as possible, and this has an effect on the design of the turbo pumps. The propellants will be of the different densities, and the mixture ratio is quite far from 50:50. So the pump of each component has to be individually sized according to the ratio, particularly the mixture ratio and the densities of each and individual fuel and oxidizer combination for the rocket engine that we will be designing. The changes in mixture ratio, that is during the flight, or minor adjustment to keep the ratio constant, like say controlling the valves, or which in turn controls the mass flow rate of the fuel that is being getting out, which require the pumps to be controllable individually. The propellant may be corrosive or cryogenic, or they may have other properties that are not compatible with simple engineering. For example, hydrogen leaks vary easily through the gaskets as well as the seals. Mass limitations prevent the use of the redundant delivery systems, and so the reliability is also of paramount importance. The propellant tank should be thin walled to reduce the dead weight, but have to be stiff enough to transmit the thrust up to the rocket without the need of an additional support structures. The propellants also have to deliver to the turbopump at a quite high pressure, which to prevent the cavitation. For the both of these reasons, it is convenient to pressurize the propellant tank to 5 to 10 bar, although this is far too small to deliver the propellant to the combustion chamber for a higher thrust engine. So this pressure is provided by a separate compressed gas supply, generally a inert gas, helium or nitrogen, that are stored on board, and one of the propellant is converted to gaseous form by heating of the combustion chamber and used to pressurize tanks. Two sets particularly. In order to pressurize tanks, either using inert gases, particularly helium or nitrogen, or heat up the propellant to pressurize the same tank, right? Now this pressure can also be supplied by bleeding off into the drive propellant tanks or some of the gas used to drive the turbines, and the temperature of this particular gas needs to be kept low, so some cooling may be needed before introduction to the tanks. This is based on the type of gas that we will be considering for the usage. The gas generator, which provides the high pressure gas to drive the pumps in a miniature combustion chamber, particularly burning part of the propellant supply, it needs a separate igniter, and this has to be supplied with propellant usually by a branch line from the turbo pump itself. Right? Usually in a previous class what we have discussed, we will be having my propellant tanks, particularly fuel and oxidizer. Right? These are taken out right, being this pump, turbo, the pump, you're having small gas generator that takes either from this case or in our small part from this turbo pump as well as this. Right? As they will be getting, they will be converting into combustion chamber for combustion. Right? Now, a separate igniter is required for this particular gas generator. Right? The propellant that is being burned in a gas generator that represents some amount, particularly a small percentage of loss of thrust, as to be also included under the mass ratio. The mass decreases as a result of the gas generator operation, but the thrust has not supposed to be counted because it is just used to run your pump, particularly turbo pump, which then drives the turbines to pull the propellant towards your combustion chamber. Now, some of this loss can be recovered by exhausting the gas after it has driven the turbine through a proper miniature nozzle in order to develop some additional thrust. Right? The natural temperature of the burning propellant in the gas generator would be approximately close to that of the main combustion chamber, but rather too high for the turbine blades. Sometimes water is injected into the gas generator to reduce the temperature of the emerging gas, or a very fuel-rich mixture is used, which achieves the same result. A fuel-rich mixture, particularly a lean mixture, which is also less corrosive, and basically a former measure requires a water tank on board. The latter implies the waste of propellant, but both do reduce the efficiency of the rocket in terms of dead weight as well as the use of excess propellant, particularly the fuel. Some rocket engines with turbo pumps do make use of the propellant that is being evaporated in the cooling of the combustion chamber to drive the pump. This saves the mass of the gas generator, but generally it results in a lower inlet pressure and is suitable for my low thrust engines. For modern high thrust engines, the inlet pressure needs to be in an order of 50 bar, and this requires the gas generator powered turbo pump and the turbines which are most efficient when hot gas inlet and exhaust pressures are very similar when used in electrical generation or on ships. For example, many stages are used in different sized turbines, each with a small pressure drop to make the most efficient use of the energy that is being sent out. Simple example. Right? When high pressure and high temperature gases are sent onto a single set of turbine, particularly a high pressure turbine, as soon as it takes out some amount of work, the same gases are sent out to my second stage of turbine, which operates under less nominal pressure than your preceding turbine, and this goes on to extract the energy that is more efficient compared to your previous single stage turbine. Now, if the turbine exhaust, particularly in case of rocket, were directly go into ambient, then the pressure ratio would be too large as well as the efficiency would be too low. Why? Because the combustion pressure, the pressure that is being occurring during combustion, right, during combustion will be high. If it's operating under certain level of area, particularly at the time, the pressure ratio compared to ambient would be large, because the ambient pressure will be less and the combustion pressure will be. This difference is too large, and which results in the efficiency, low efficiency for your gas generator cycle. This can be overcome by utilizing a multi-stage turbine, but the extra, as we add the number of extra stages, it adds the weight to the overall rocket, and this is therefore necessary to reach a compromise between the stages as well as the multi-staging of the turbine. And an important variant of a gas generator system is the staged combustion system. The exhaust from the turbine enters the combustion chamber instead of ambient. This has two advantages. That is, the pressure ratio for the turbine is more compatible with high efficiency, and the remaining energy in the turbine exhaust contributes to the main combustion chamber, ultimately to the thrust, where the exhaust from the turbine is used directly to generate thrust, and the efficiency is low because the temperature at the nozzle inlet is much lower than the main combustion chamber, right? The exhaust velocity depends on the square root of the combustion chamber temperature, which we already know. So, if the exhaust from the turbines is allowed to enter the combustion chamber, then the residual heat that is being contained in the gases that contributes to the heating of the combustion products that are already available in the chamber, right? This acts as a type of igniter, which provides a way of using the waste heats that is being generated in the gas generator cycle and creating a much more thermodynamically efficient cycle. An engine which do this in general produce a higher exhaust velocity for any given thrust, while the turbopumps driven by gas generators are widely used. There are other methods for providing the hot gas that can save it complexity by making use of the gas created by regenerative cooling. Right? What is the regenerative cooling? We'll discuss. That is particularly a propellant. In our case, we'll consider liquid hydrogen that is passed through the cooling channels of the combustion chamber. Right? The pass through the cooling channels of the combustion chamber as well as the nozzle. Right? As they are being passed through, as they absorb the heat, they turn themselves into a hot gas, which is diverted into to drive the turbine. In some cases, only one turbine and oxygen pump is divided. There is only one turbine, and the oxygen pump is driven by a gauge chain that is being placed. Right? Let us understand this a bit, particularly regenerative cooling. We will be having, in our case, liquid hydrogen. First, we will understand how the temperature of this particular liquid hydrogen is less. In order to maintain the hydrogen in liquid state, what we are supposed to do? We are supposed to bring the temperature down to its liquefaction temperature. Right? So, hydrogen below this temperature will be under liquid state. Right? Now, as we are maintaining the hydrogen under liquid state, which means we can enmass or we can maintain the huge amount of fuel, particularly liquid hydrogen, in a shorter amount of shorter space. As the temperature drops, the volume also drops, giving us a small concise area within which we are supposed to store our liquid hydrogen. Now, coming to your regenerative cooling, when we are storing the hydrogen under liquid state, the temperature of it is too less, right? And in order to combust, right, in order to maintain its combustibility, we are supposed to again reheat the same, right? reheat the same. So in order to reheat the same, what we will be doing, we will channel the liquid hydrogen through a set of cooling channels, right? Set of cooling channels that are arranged in such a way that it passes from the combustion chamber towards the nozzle as well as the nozzle. Now, as it passes through combustion chamber as well as the nozzle, it converts itself, absorbing the heat from the combustion chamber and nozzle valve by itself and converting your liquid hydrogen to a gaseous hydrogen, right? Now this gaseous hydrogen is diverted to drive the turbine, right? Now the turbine is again rerun to push furthermore amount of propellant towards the combustion chamber. Now there are two cases. One, we can use the same gas to drive two separate turbines, one for propellant, one for oxidizer, particularly liquid hydrogen and liquid oxygen, to run separately, or in some cases only a single turbine can be used to, and for the fuel as well as for oxidizer pump we'll be using a small gear chain connection between the turbine and your other oxygen pump. In other, particularly, there are two turbines which are ordered in series, and with the hot hydrogen emerging from one turbine and flowing the second, the exhaust gas is sometimes then diverted from the combustion chamber to recover any remaining heat. In this system, but because of the simplicity, was used on early engines and now being specified again for upper stage engines to reduce the cost and mass associated with the separate gas generator. This system is sometimes described as a topping cycle or an expander cycle, and which has many variants. Regarding the cycles, particularly related to your propellant distribution cycles, we'll discuss further again in detail each and every cycle to understand it better, particularly the thermodynamic effects of the same. Now, coming to your term cavitation. Previously what we have discussed, any propellant, particularly propellant tanks and turbo pumps, right? These turbo pumps will undergo a process or a phenomenon called cavitation. We'll understand what is by cavitation in how the same thing is being affected for our rockets. It's a well-known problem that occurs particularly for any liquid that is in contact with the rapidly moving vane. On an instance, particularly a ship propeller. What happens during this? The pressure that is in the liquid at a retreating surface of the vane is reduced and can be low enough to allow a local boiling to take place. For example, let's consider this as a vane. This is moving or rotating at the speed that is higher, and this is my liquid surface area, right? As the vane is moving at a faster pace, the area, let me just right, the area near to the blade will have its local pressure, particularly the pressure near to the vane surface gets reduced so enough that the water, particularly the water particles that are being around the vane, tend to boil, right? As the pressure drops, the water, particularly the water molecules expand, which creates the boiling effect. Now, as the boiling takes place, the bubbles of the vapor are produced, right? And they then collapse when they enter the region of any normal pressure. The tiny shock waves that are being produced, which damage the surface of the vane, particularly plate, and a severe cavitation can produce significant quantities of vapor at inlet of the turbo pump. This is very quickly reduces the efficiency of liquid transfer as the rotation speed increases, the larger the regions of the vapor appear. Particularly for turbine engine rocket pumps, the rotation speed is very much high, particularly 10 to 30,000 rpm, which is very typical, and the liquids that are quietly likely to be cryogenic. These are the ideal conditions for cavitations to take place. Particularly, a damage to a vane surface may not be too serious for a single use pump, but if a significant amount of vapor forms, then the turbopump will race due to its reduced load, and damage to the bearings as well as the other components might take place. The flow rate of the propellant which also suddenly decrease, and with a consequent drop in thrust, which in most cases will lead to a disaster, and this is a very serious problem. And to avoid the cavitation, the pressure at the inlet to the pump must be kept high enough to prevent local evaporation of the liquid, and this can be made possible under several ways. First thing is to maintain the static pressure. The static pressure in the propellant tanks may be sufficient, and the acceleration of the rocket can generate additional pressure at the pump inlet. And if the propellant is reasonably dense, the supply lines are axial and sufficiently long. This is likely to be the case of liquid hydrogen, where it has a specific gravity of 0.07 and where other measures cannot be succeeded. And particularly where the pump speeds are very high, a two-stage pump is required. The low pressure pump, which is often called as an impeller, simply has a task to raise the inlet pressure at the main pump to an acceptable level, say 10 to 20 bar. Therefore, it is rather simple design, but if it's mounted directly on the inlet on the same shaft as the main pump, it may not be possible to avoid cavitation because at the impeller blades, if the shaft's speed is very high. Some improvements that can be realized by correct shaping of the impeller blades, although they may need to driven by a gear train. A second concept, particularly pogo. Naming wise, it might reason unsoundly, but we'll try to understand the concept to understand it better. The pressure at any inlet of a combustion chamber should be constant for a steady flow of propellant towards the combustion chamber, hence giving out the steady thrust. But the acceleration of the rocket that raises the pressure at the pump inlet, right? Propellant, the rocket is moving in this direction. What happens? The fluid, based on its density, let's say we are calling it as by gravity or by force or the thrust that is being generated, it tends to have the higher pressure at the inlet, pump inlet, and it's possible to develop a feedback loop within the instantaneous thrust as well as the pump inlet pressure. If this happens, then a small natural fluctuation in the thrust, which will result in the fluctuation in the flow rate of the combustion chamber. This fluctuation will make itself felt, and with a slight delay as further fluctuation in the thrust. This in turn changes the inlet pressure at the pump, and which causes another thrust fluctuation, and so on. The time delay, which is usually 10 milliseconds in a region, and the reinforced mechanism can result in the buildup of oscillation in thrust with a period of about 100 Hz. This is very damaging to the rocket as well as the payload, as a small fluctuation in meganewton of thrust is a large force. For this reason, pogo correction systems are fitted to liquid propellant rocket engines. Why does the pogo is not relevant to your solid? Because the propellant systems, particularly the propellant, are the charge that you are considering for solid rocket propellant motors. You will not be having any movement for the propellant during its storage or during its movement. Only thing that it gets eroded or burned itself over a period of time to give your thrust out. For liquid engines, the fluid that is constantly under motion, either in positive or negative direction based on the thrust and the movement of the rocket. The basic principle is to introduce some capacitance systems in order to smooth out the fluctuations, particularly under inlet pressure. A small sealed volume that is being connected to the propellant line adjacent to the combustion chamber inlet and is filled with propellant. It is pressurized using the gas from the tank pressure system. If the line pressure fails momentarily, additional propellant is very quickly injected from the storage volume to raise the pressure to its original value. If the pressure rises, then some of the excess propellant flows in the sealed volume, again restoring the line pressure to normal. It is usually only necessary to fit pogo correction to one propellant line, which is in most cases the oxidant line. The system can be passive or it can be actively controlled to deal with, for example, such greater pressure fluctuations which occur when the engine is being shut down or is being started. For such cases, the power correction system can also protect the turbine from the cavitation. For a single-use engine, damage to the turbines at the shutdown is of no consequence. But for reusable engines, a turbine damage due to racing into a heavily cavitated fluid is a serious matter that is to be concerned, right? So in the next class, we will be discussing regarding your propellant distribution system, particularly the types, what are the forms, what are the structures, and in what way we can arrange your tanks, and what are the thermodynamic cycles. All these things we'll be reading under your next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.